In this video, we'll talk about the elastic curve, the curve that describes how the central axis of a beam bends when it's subjected to a load. We'll derive the differential equation of the elastic curve, which is key to calculating beam deflections. To illustrate the concept, let's look at a clamped beam, as the one shown here. First, it has this line that represents the center line of the beam, and also these other gray lines that represent the entire cross-section of the beam. Again, this white line is the center of gravity line of the beam. We will apply a 1 kilonewton force at the free end of the beam, and under this load, the beam will deform. Now, keep in mind, according to Euler-Bernoulli beam theory, these equations are valid for small deformations, so the deflection you see here is exaggerated, just to make it easier to visualize. Also, in reality, the entire cross-section of the beam deforms, so this is the actual deformation of the beam. But the elastic curves describes the deflection of the centroidal axis of the beam only, so this white line that is shown here. Now, let's set up our coordinate system. Here, I'll take the y-axis pointing downward. This isn't universal or adopted in all textbooks, but the difference at the end is only a matter of sign convention. Now, imagine we want to know the deflection at every meter along the beam. So this distance is d1, d2, d3, and d4. How do we calculate these? That's where the elastic curve equation comes in. Not only can it give us deflections at specific points, but it also gives a continuous function v of x, meaning we can find the deflection anywhere along the beam. We will now proceed with the derivation of the elastic curve governing equation. For that, let's zoom in on the end of the beam, as shown here. On the top of the screen, we will show the undeformed shape, as shown here, and on the bottom, the deformed shape, as shown here. We will define v of x as the downward displacement of the centroidal axis. According to the Euler-Bernoulli hypothesis, plane cross-sections remain plane and perpendicular to the axis. So after deformation, we get the pink cross-section you see here. The derivative v prime of x represents the rotation of that cross-section. Now, let's define u of x as the displacement of a point located at a distance y from the centroid, in the x direction. Because the point moves opposite to the positive x direction, we can write u of x equals to minus v prime of x times y. Now, we will recall the concept of strain. Let this be an element of size L that deforms delta L due to some applied load. In undergrad, we see that strain is defined as delta L over L. We could also say that the displacement u at a point L over the total length L represents the same measure. Let's now recall the first equation we derived, u of x equal minus v prime of x times y. The equation on the right only works for elements with constant strain. More precisely, the strain in the x direction is defined as the derivative of the displacement function with respect to x. We now derive the first equation with relation to x, and by joining both equations, we arrive at a relation between strain in the x direction and the second derivative of the deflection of the beam. Let's keep this equation on the corner for now. According to the Euler-Bernoulli hypothesis, a plane cross-section remains plane. Consequently, if we adopt Hooke's law, the stress in the x direction will vary linearly along the y-axis. Adopting the following y and z axes, we can imagine a force differential applied at points of the cross-section as shown by the yellow arrow. Now, we will adopt the following convention for a positive moment. So, a moment that goes counterclockwise is defined as the positive direction for the moment. In this case, the lower part of the cross-section will be under tensile stresses, which are shown in red, while the upper part of the cross-section will be under compressive stresses, shown in blue here. Now, recalling Hooke's law, where sigma equals to the Young modulus E times epsilon, and now substituting epsilon from the corner equation, we get the following expression for the stress in the x direction. Additionally, the moment along the z-axis can be calculated as the force differential F times dA times the distance of this force to the CG. Note that this area integral is on the y and z axis only, therefore it does not depend on x. By plugging the above equation into the bottom equation and assuming a constant modulus of elasticity, both E and V double prime can go out of the integral, and the area integral of y squared is simply defined as the moment of inertia of the beam, in this case Iz, leading to the following expression. By taking mz to the right-hand side of the equation, we arrive at the elastic curve governing equation. Traditionally, we call mz as m and iz as simply I. This is a second-order differential equation for v of x, the deflection, that can be solved by integrating 2 times and using the boundary conditions of a bin element to determine the integration constants. And this is it for the derivation of the elastic curve equation. Thank you for watching.